Ready to start off with introductions. My name is Chris Archambault, and I'm a computer engineering student.
My name is Neil Lighting, and I'm a EE student.
My name is Nathan Hufsteller. I'm also a double E.
My name is Jay Lee. I'm also a double E.
And I'm Will Novak, and I'm a CE.
All right, so there's kind of an agenda as to what we're going to be talking about today. We'll start with the introduction, introducing what our project is, and then we'll work into going over the design specifications set by our employer, followed by some initial design concepts, our final solution, and then a risk analysis, a budget talk, and we'll summarize everything for you at the end. All right. So our project is to make what Bosch called an automated power mode test system. Now what that means is it's essentially just a power supply which you can program to emulate certain voltage waveforms. And how we propose about going about this roughly is showing you preliminary is we have our transformer and rectifier like you find a typical power supply. And after the rectifier you see what's called a buck regulator, and that's what the circuit will be using to regulate the voltage, and Chris will talk more about that for you. We'll be using this with a microcontroller, the same one we've been using in lab, as a way of interfacing with the PC, and also to work as a PID controller to help control voltage and monitor it. Here's a couple of waveforms as examples for what we need to replicate. What we specifically need to do for them is they want us to replicate a car's cranking profile. What they do is they're a multimedia division, and so they have their own ECUs, their computers that they want to test against the cranking profile. And as you all probably know, when you go to really low voltages and significant drops, you could harm computers, memory, registries, so on and so forth.
So for the design specification, so both require us, because it's testing for the ECU systems, so the battery for the car is 1 to 18 voltage range and 1 to 10 ampere range. So it's also for the lab use. So it's we need a USB interface to PC. So we need to program our PID controller using the PC, and we need a 4 to 8 channel relay for test bench interfacing, mechanical idle for voltage and current adjustment, scramble to interface with CN and MOSFET. Following our cranking profiles. So because the car are different, so we need different cranking profiles. Like we have we have about 30. They give us about 30 different kind of signals. So based on software, it's based on the C microcontroller code. And it's based on the Windows XP and 7 environment. So it's also accompanying UML style documentation.
I will talk about AC to DC rectifier. That is a leader.
And then buck regulator, and then the power supply control is part of our hardware solution. First is the AC-DC rectifier circuit.
I will discuss about the transformer and AC to DC rectifier, bridge rectifier. It is a basic but important part because everything else in the project depends upon it, and our project needs 20 volt DC from 1 120 volt AC wall outlet. And by using transformer, we can the transform ratio is 5 to n, so we can reduce almost reduce to 20 and grid 2 volt, and grid rectifier can change from AC to DC. And also we need 15 amperes capable of supplying it, and components should be hardwired.
One of the main things we wanted to consider is circuit protection. This hardware will be running overnight, so we wanted to ensure that the devices they hook up, since a lot of them are concepts, that they are protected. So to do this, we implemented reverse battery protection, over voltage protection, and also current protection. And this is just a basic block diagram. We just chose to use a single diode instead of another MOSFET for reverse battery protection. The TBS diodes help for transients, and also over voltage protection. And the one on the output has to be sized out of the limits that the output will actually see, because the whole purpose of this project is to actually create the transient responses and transient voltage conditions which cause problems. To do this, we chose a buck regulator circuit. We also considered a voltage regulator using low dropout voltage regulators. Ultimately, we use this for the efficiency and simplicity of control. It also has a lower power consumption relative to the low dropouts. And then the control of it, our duty of our MOSFET directly correlates to an output voltage, so it'll be nicer to program. And then it's also capable of the range of 0 to 18 volts which they want. And the goal is to have a maximum switching or minimum switching frequency above 100 kHz. And the reason for that is to filter out some of the ripple. This is the basic schematic of our rough concept. The reason why we have arrays of capacitors are because our loads are very unknown. With this setup and all the transients, we have to be able to drop from voltage around 14 volts to 0 volts and back up to 8 volts all within 4 milliseconds. So obviously any energy storage devices may cause that condition to not occur. And then, as I said, with the transients with the buck regulator, you're switching it on and off, so it's smooth through the inductor and the capacitor, so the current doesn't see quite the same ripple, but we don't know exactly what the load's going to be. The average is probably going to be around 5 amps, but they could hook anything up from just one LED all the way up to an infotainment system with speakers. So the thing we have to consider is the effect of switching. If we don't switch fast enough, we'll end up seeing these transient ripples, which aren't normally seen from a regular battery. And then this also shows the 1/10 scale duty of kind of the simplicity of the control is we just have to vary the duty to follow that, and we'll also be PID control. We also instrumented the circuit with Hall effect current sensors. They have a lower voltage drop and no series resistors relative to other current sensors. And we use those for the control and also current protection. With the additional voltage outputs that we have to power other devices that they may want to use, this is going to be used on a test bench. And we also have their communication equipment that we have to power also. So having the current protection and that flexibility that's all programmable is a nice feature.
So our system is based on use for the lab testing the ECU systems, and so we have a general power supply for the 120 volts. So based on this, it's a 10 ampere system. So from the AC to DC, our circuit will be hardwired. So also we need an area for everything connected. So the microcontroller and the clock regulator will be on a printed circuit board. So and each have to be easily connections. So and also for the high power, we need internal fan for cooling to make sure every component will work well.
Now, as Chris was saying, the way that we're going to get this whole thing to work is by varying the duty cycle of the buck DC circuit. And the way that we're going to do that is with a microcontroller sending different pulses to the MOSFET pin to adjust the duty cycle. So the way that's going to work is with a PC application where you load the profiles into it, and then it's going to be sent over USB to the MCU firmware. So the PC application, according to Bosch specifications, will be written in C#.NET using the Microsoft Visual Studio toolchain. And it needs to be scriptable so that Bosch engineers can load up profiles and determine how many times those profiles are going to run, also, and however many different profiles that they want to run as well. So basically it's going to be able to parse CSV wave data, which is just going to be voltage versus time metrics. And the PC application is going to send that information in real time over USB because the available on-chip memory of the microcontroller is not large enough to handle all the data within the CSV. And then also after it goes to the microcontroller sends the pulses to the MOSFET and we simulate the wave profiles. There's going to be internal traces within the device under test, which is going to be the infotainment ECU and possibly the test bench. And we need to record those within the PC application as well. And moving further, we may possibly be interfacing with CAN or MOS, and if we don't, then possibly next year's design team will. So we need to make it scalable such that we can interface with CAN and MOS buses. Now the other side of it is the microcontroller firmware. As Chris stated earlier, we're going to be running on the same microcontroller as what we're using in lab, which is super convenient, and it's going to be written in the C programming language. Essentially what's going to happen is it's going to read the voltage metrics, voltage versus time metrics from the USB connection, and it's going to calculate the pulse frequency to get the required duty cycle to simulate those waveforms. Now there are several risks associated with this project. First of all, if we simulate the profiles wrong and we send crazy spikes through, we're probably going to damage the test device. So that's why we have all those safety measures in place. And then also, since it is a high voltage, high current system, there's always the possibility of overheating. So our enclosure needs to be designed such that that doesn't happen.
All right, budget. All right, our costs come almost exclusively from the hardware. We don't have any much like licensing costs or anything just to design it. And I'm going to break it down in a couple of sections for you. Keep in mind that this is just a preliminary budget. There's still some unforeseen costs that we haven't calculated out yet because we haven't really been able to. But I'll talk about those when we get there. All right, first part, power supply. So this is going to, so right here you kind of see layout of what our costs are going to be lining with power supply. Greatest of which really right now is the MOSFET, which is $15, which is necessary because it's a high power MOSFET and it's going to be running all the current through a device through it. It's going to be our main source of turning on and off the entire device. Then the total for the power supply ends up coming to $56.38, as you see on the bottom. All right. Current sensor and voltage regulator are put together since they're both kind of like circuit elements and are active part of their device. Current sensor primary cost will be the sensor itself, ranging at $14-ish, and our voltage regulator. Our main costs are actually going to be coming from the PCB traces. We needed to use the PCB traces just because we're dealing with, it's the easiest way to deal with high powers And so, as you can see, that's our highest cost there. So those totals come out to $1688 and $95.45. Last part, controller and interfacing. So primarily just the PIC, and we'll have to have a USB interface as additional cost to interface with the PC. This brings our whole total to $176.28 as it stands now. Most of these parts will be acquisition via DigiKey or Mouser online ordering. It seems to be the most reliable source for us right now. And this is just, like I said earlier, it's a preliminary cost, so it'll probably be higher because we haven't accounted yet for shipping charges on these things. And we haven't done a whole lot with the enclosure yet because we need to really get better dimensions on what's actually going to be involved. I mean, the fan, the transformer, the PCB traces. While we have most of these things figured out, it's kind of hard to get a good sense for how big the enclosure's got to be. So shortly we'll have that.
Oh, we skipped over the summary, but there we go. Pretty much there's two components, and that's the hardware and the software. The hardware is going to be the rectifier. That's going to lead to the buck DC, and that's going to lead to the device under test. And that is going to simulate the waveform profiles from input into the PC application, sent over USB to the microcontroller, thus sending pulses to the MOSFET and simulating those profiles. Timeline and budget, the timeline is good. We're going to be able to finish on time. The budget is not finalized yet, but we do have a good idea that we're going to be under $500, and that was our goal.
We are also starting this project from scratch. There hasn't been too much done relating to this. There are some alternatives which are really expensive, you know, upwards of sometimes around $100,000. So that's why Bosch reached out to us to design this for them. They don't need the functionality of all the expensive equipment, and we are the first team right now to do that.
Does anyone have any questions?
Thank you.